So first of all, any questions from Tuesday's class? You'll notice that homework 1 is posted. It's a bit long. You might want to take a look at it, get going. And there'll be more notes going up soon. We want to get through this background stuff. I'm going to finish the function spaces stuff, and the concentration measure we'll do fairly quickly. And then we get to start getting to the meat of the course. In particular, like we're going to do high-dimensional linear regression will probably be the next topic. OK, so remember we left off with we were constructing these reproducing kernel Hilbert spaces. You choose some kernel, which you could think of intuitively as measuring how similar two objects are, x and y. But the question is, how do you build up a function space out of that we're going to use for, say, classification or regression? And it's always good to have a concrete example in mind, so I would keep the Gaussian in mind. That's the most commonly used example. And here's how we're going to do it. Here's the recipe. So this is a function of two variables, but let's temporarily fix one of the variables and think of it as a function of the other variable. So for example, if I think of x as fixed for the moment and just think of it as a function of y, well, in the normal, what is that? That's a normal with mean x, right? In fact, we might even call that, sometimes I'll write it like this to indicate I'm thinking of x as fixed. I'm just fixing one of the coordinates. And if I do that, in fact, let's pick a few numbers. So k, suppose I just pick, let's say, L points and fix them. So now these are just functions of the second coordinate. I get some functions. OK, so think of those numbers that I just fixed as parameters. I just fixed these parameters. Now I just have functions. It's no longer a function of two variables. It's just a function of one variable. And I pick some finites out of them. That just gives me a bunch of functions. In this case, they just a bunch of normals. And now I'm just going to take all possible functions I can get that way by taking linear combinations. So we're going to take h0 to be all such functions, all functions of the form f equal to, let's say, hj kxj y. And when I write this set, I mean all possible choices of these centers that I could have fixed. All possible choices for the number of them could be 10, 20, 30, 40, all possible values for these coefficients. So I'm just think of them as, in other words, as they're basis functions, and I'm just taking all the possible linear combinations of them. That's the function space we're building. Yeah.
This is relative to a particular kernel?
This is all for a given kernel. Each kernel is going to generate a different space. So now I've defined a function space. So in this, you can think of it in this example as it's linear combinations of normals. Remember, those alphas could be negative too. So this is not, I get some of these up and some of them below 0 and so on. Just linear combinations of basis functions, basically. And you can see how the kernel shape is going to determine something about this space. But we need to define an inner product and a norm, and it's going to work like this. If f can be written as some linear combination, by definition, any function in this space can be written as some linear combination like this. And if I take some g, which can be written as a different linear combination, possibly even a different number of basis functions, and possibly at different locations, let's say yj. Any two functions like this, right? By definition of this function space, any two functions are linear combinations. I'm going to define the norm. And now we have to be really careful because a lot of us have a tendency to just write this sort of the inner product, not the norm. A lot of us write it like this, but to be careful, we should write it like this, that it's with respect to a particular kernel. Yes? xj is, remember, we're picking j. So there's x1, x2, x3. We've picked a finite number of points to center these things at, roughly speaking, arbitrarily. Those are like parameters of this function. Again, keep the normal example in mind because it's just like picking the means of the normals, basically. Okay, so I might forget to put the k here, but remember we're defining an inner product here with respect to this kernel, and it's defined to be, so the definition is not the usual inner product, it's the double sum of all the coefficients times the kernel at those two values. Did I use I and j? Yeah, I and j. So let's just think about that. I just took f is some sum of these normals, for example. They don't have to be normals, right? G is some sum. I'm just defining the inner product to be, in this norm, to be, take their coefficients and multiply them together. But every time you do that, take the kernel value that corresponds to that xy and that yj. And one thing you can check is that this is a well-defined inner product, because I haven't told you, if I write f this way, maybe there's another, I could write it as a different linear combination too. Who says it has a unique representation? But it turns out that you can show that the inner product is still well-defined. You get the same number regardless of which representation you write. So this is a well-defined inner product. And of course, it defines a norm, namely the inner product of f with itself. So now we have a class of functions, and we have a norm, an inner product and a norm. Okay, and this is going to be our space. Actually, we're going to take the completion of this space under limits, and that'll be our reproducing kernel Hilbert space defined by this kernel. All right, so, but why is it called a reproducing kernel Hilbert space? Actually, let me just pause for a moment and just say, is it clear now how we're defining the functions in this space? We're using the kernel to generate things that you can think of as just basis functions. We take all linear combinations. That's our space.
So we're allowed to use any number of kernel functions to get the function that.
That's right.
So it could be uncountable, like in theory.
Yeah. Well, you would usually do that by taking limits, but yeah, it's right.
Why we define the sum but not integral?
Well, I suppose we could do it that way, but this is the way it's generally defined, is we're going to be working with finite linear combinations. Okay. All right. So this is just some definition, right? I've just somehow made up some class of functions. We don't really know what they look like yet. Yeah.
So when you define f and g, actually in f you're fixing x, and in g you're fixing y.
That's right. So think of it as, to specify a function, I have to pick some parameters. The parameters are the coefficients and the first coordinates of these guys. And they're different. For any function, I can pick different ones. So in this case, I pick different ones. That's right. It's arbitrary. So again, just think of it as arbitrary linear combinations of normals. That's the way to think about it. I don't want to harp too much on the normals, because I don't want you to think it's only normals. But that's just a good one to always keep in mind, because it's simple and intuitive. And I think you can see that if I mix a lot of these together, I can get lots of different shapes of functions, right?
So I think I missed this. When you define that space H0, the K is fixed.
No, it's also over. Oh, the kernel is fixed?
Kernel is fixed.
Yes.
But the Xi's are not.
Right.
Okay.
Right. Every possible choice of xi's generates a new function.
That must be in the same function space that you take inner product during two linear combinations.
Well, no, the inner products are just these. They're always based on the kernel. They come from these kernels.
So, but that must come from the same kernel, or it can.
Yeah, this is always for the same fixed kernel k, yes. So we're starting with one fixed kernel. That's what's generating the space. Okay. Okay, so, but let's verify some, so this is a little bit mysterious if you've never seen it before, because what properties does this function space have? And in particular, what we're going to see is that the norm here is actually a kind of a measure of smoothness, and that's not obvious at first, that the bigger the norm, wiggly functions tend to have a bigger norm. That's what makes this useful. But let's back up and see some properties that this space has. Okay, so first of all, it has something called the reproducing property, hence the name reproducing kernel Hilbert space, okay? Which turns out to be a very handy property for proving things, for computing things. And here's the reproducing property. Suppose I have f. So again, we know it's sum. Did I use I or j here? I of these kernels. Now here's an interesting thing. The function k sub x, what is the function k sub x? Remember, that's just the kernel where x is treated as fixed and the second thing is treated as a free variable. So that's, in our normal case, that's a normal distribution. That's also a function in our space, right? It's a linear combination of one thing, the kernel. And so that's an example of a function. In other words, it's like taking the number of things in the sum to be 1, and it's like taking alpha to be 1. Then you just get that kernel. And in particular, there's nothing to say I can't take the inner product. But this is a function where when I take this double sum, the second thing is the kernel. Again, that's like having only one thing in the sum and beta is equal to 1. So if I take this sum, I just get back f. Right? I just get back, by definition, alpha I k. Let me make sure what I did was clear. I just took the second function I'm taking to be kx. I'm thinking of that as a function in the space. It's beta times kx, where beta is 1. Okay, it's just itself. And so when I take this double sum, somewhere, there isn't a second double sum. So I just get this formula. But that's the definition of f, of x. In other words, if I take the inner product of a function f with one of the kernels, I get back f at x. It reproduces f. That's the reproducing property. It's very cool. It turns out to be very useful, and it's going to be the reason, you'll show this in the homework, that convergence in norm does imply pointwise convergence in this reproducing kernel Hilbert spaces. This is the fact you'll use. And if I take the other function to be a kernel, why not? Let's just look at kx with itself. We just get back this, for example.
This kx, what is x? Is it any x?
Right, remember that. So this is a function of two variables, but if I fix this at some arbitrary fixed value, I'm writing it like this. So I'm thinking of it only as a function of the second variable with the first value fixed. Arbitrary point.
In the first equation, there are 3x. No, at the second line. Yeah.
There's a fixed x here,
Yeah.
fixed x here, same x.
So fx is that x is the same as the
Yes,
x.
right. Yeah. So the inner product of the function f with the kernel centered at x gives you back the value of the function. For those of you who've taken some functional analysis, you'll recognize that this is saying that this is the evaluation functional.
So does that mean that x has to be in the domain of the app where x...
Everything is on the same space. You're right. So I'm talking about, let's just to fix things, we're on some subset of the reals or something like this, and everything's defined over whatever set we're working on. The kernel's defined on that space. The functions are defined in that space, right?
Graph is well defined on the interval to 0 to 1.
Right, for example.
So just to be clear, so if we want to evaluate f at x, we just take the inner product of f with the kernel centered at x.
That's right. That's a pretty cool property. Right. And that's exactly right. If I wanted, that's not how you would do it, but if you wanted to take f and evaluate it at x, that's equivalent to taking its inner product. But remember, it's not any old inner product. It's this new inner product. Okay. Okay, and so the space we get is the completion of H0. What do I mean by the completion? I mean if we take any limit, we include all the limits. So if we have a norm, so we can say if fn minus f in this norm goes to 0, then fn is converging to f. So whenever we're talking about a space like this, when I talk about fn converging to f, we mean in the norm. And we can form the completion, which means the smallest space containing H0 and its limits. That's the reproducing kernel Hilbert space generated by the kernel. And it's such a Baroque Byzantine definition that at this point you think, why is this even useful? And if you're used to working with them, you know why they're useful. If you've never seen it before, it seems like this is a pretty complicated way to define a space. But they have a lot of nice properties. And a lot of the familiar spaces are reproducing kernel Hilbert spaces, even if they're not expressed that way. The Sobolev spaces we talked about earlier are reproducing kernel Hilbert spaces for a particular kernel. We'll get to that. So here's some things you might want to check. These are not hard to check. There's only one that's a little bit tricky. We'll actually do it on the blackboard, which is, how do I know, again, that this is a well-defined inner product? So you can check these. And remember, I keep leaving out the subscript k. I've even done it in the notes. I apologize for that. But when we're talking about a reproducing kernel Hilbert space, I should always, if I was careful, put the sub k. But you can check very easily that this is true, not surprising, that the linear property for the inner product is true. Okay, nothing surprising here. The only one that we might want to think about, because this is a crucial one for inner products, is that the inner product of f with itself is 0 if and only if f is the 0 function. And so let's actually prove that. It's only one line long, so let's prove it. Well, first of all, this direction's easy. If f is 0, it's not hard to show. This is 0. But how do we show that if the inner product of f with itself is 0, that f is 0 everywhere? And we're on the top of page 12 here. It's just this. We're going to say this. 0 is certainly bigger than or equal to, let's take f evaluated at an arbitrary x and square it. By definition, that has to be non-negative, so it's bigger than or equal to 0. Now we're going to use the reproducing property. This is equal to, I've lost it. The f of x is equal to f inner product with the kernel. And it's squared. So it's twice. Okay? Something I should have also said is we can check that the Cauchy-Schwarz inequality holds. So remember, Cauchy-Schwarz says that this is less than or equal to the norm of f times the norm of the kernel. And it's the same thing here, so that's squared. But the assumption was that the norm of f is 0. So I've got that f squared is bigger than 0, less than 0. That implies f is 0, and that's for arbitrary x, so therefore the function is 0.
So we always assume that the norm is the one that comes from the inner product.
Yeah, everything here, right, has to be consistent. So the kernel's always fixed. I'm always talking about the norm and inner product corresponding to that kernel. I should be more, I should really be more careful and be writing like sub k everywhere and everything, yeah. Yeah, you can't be switching norms and things. Let's see, is that something you're going to show in the homework? Yeah, one thing you'll show in the homework is this thing I talked about earlier, which is telling you that these reproducing kernel Hilbert spaces must have are functions of nice classes of nice functions, which is this property I just alluded to, which is that the evaluation functional is continuous. Let me explain what I mean. So I talked about this on Tuesday. So what is the evaluation functional? The evaluation functional, you think of it as an operator that it takes a function. Think of it as a computer program. You give it a function, and all it does is evaluate that function at a particular x. So delta n operating on a function is equal to f of x. And normally, and like in L of L2, for example, this evaluation functional is not continuous. And that's just another way of saying that if Fn converges to Fn norm, it doesn't mean it converges pointwise, because that would be saying that this evaluation functional converges. But for reproducing kernel Hilbert spaces, it is true. If I look, so suppose I have Fn converging to F in norm. Let's just evaluate it. If I take the delta of x times Fn, because we're in a reproducing kernel Hilbert space, I know that's the same as taking Fn with kx. And there's a comma missing there. Because of the norm convergence, that also implies the inner products converge. But that's equal to f of x, which is just delta x of f. In other words, what we've just shown is that if Fn converges in norm to f, then the evaluation of Fn converges to the evaluation of f. Or in other words, norm convergence implies pointwise convergence. It's not true in general that this evaluation functional is a continuous function. Okay, but it is true here. And it's really because these are always going to be sort of well-behaved functions. In fact, you're going to prove in the homework, it's not hard, that this is the defining feature. A Hilbert space is a reproducing kernel Hilbert space if and only if the evaluation function is continuous. It's equivalent. And this can only happen if the functions are kind of well behaved, right? We saw an example last time where I took a sequence of functions where the norm was going to 0. Say the function looks like this. And then as n gets bigger, I made it like this. And I can make the area go to 0. So the integral of Fn minus 0 squared is going to 0. So it's converging in norm to 0. And yet the value of the function at 0 is certainly not converging. It's diverging. So we're ruling that kind of behavior out. That's one reason why people like working with reproducing kernel Hilbert spaces, is they're sort of nice functions.
Is this evaluation function has some relationship with the delta function?
No. Well, technically, so actually let me answer that more carefully. He asked, is the evaluation functional related to the delta function? Well, in a sense it is. If you integrate a function with respect to the delta function, it's usually defined to be the value of the function at that point. So in that sense, yes, it is. But in general, that need not be a kind of well-behaved functional, whereas here it's a continuous linear functional. But yeah, think of it as like the delta. Yes, think of it like the delta function. Like a point mass measure in some sense. Now, what's not obvious, though, is what's the relationship in general between kernels and the spaces they generate. So I have to tell you, in a lot of machine learning, people just throw down an arbitrary kernel because it's convenient and work with it. And if you say, what's the actual function space? Or what are the functions? You might not know. Okay, so it's not always easy to figure that out. Conversely, if I give you a function space and say, what's the kernel that generates this? It may not be obvious. Okay, so a lot of times these choices are really made through convenience. I'll give you a couple of famous examples of these spaces just to give you a flavor. I don't want to belabor this because I really just have already communicated all the main things we're going to need to know about these spaces for this course. But a couple of examples. Let me find a brush here. So if you remember from calculus, I can always take a function and compute, if it exists, its Fourier transform, which just measures how much energy there is at different frequencies. Okay, so if you haven't ever taken that before, let's not worry about it. But for those of you who have seen that, it's a good example that if I take H to be the set of all functions on R whose Fourier transform is supported on some finite interval. So the Fourier transform just measures, again, the frequencies. And if there's lots of oscillations, the Fourier transform will have a lot. The Fourier transform will die off slowly, saying that there's a lot of wiggles out there. think of it as just intuitively just think of taking a linear combination of cosine functions and looking at the coefficients and how they die off. And if it has a lot of wiggles, it's going to have a lot of stuff out there. But if it doesn't have anything beyond a, then that's saying it's got to be a pretty smooth function. And it turns out that the kernel function for that is sine of a y minus x over a y minus x. So it's certainly not doesn't look anything like or looks quite a bit different, let's say, than the Gaussian example. And it turns out that the inner product turns out to be the ordinary inner product, usual inner product between f and g. Okay, so sometimes you wouldn't guess, right, what the kernel is what I'm trying to say. Let me give you another example that comes up actually for us in practice. When we go to bound the bias of certain classifiers or regression functions, we're going to make an assumption like, oh, let's suppose it's one of those Sobolev spaces, say, of order m, which roughly speaking meant, what did it mean? It meant that the mth derivative squared is finite, less than some constant, let's say. That was an nth order Sobolev class. And let's suppose, we're talking about functions, let's say, on, just to keep it simple, on 0, 1. Well, it turns out that is a reproducing kernel Hilbert space. But the kernel, and this is on page 13, here it is. It's 1 plus xy plus xy squared minus y cubed 6 when y is less than x, and then the symmetric form when x is less than y. Kind of a weird looking kernel, right? So probably if you just said, I think I'll make up a kernel today, it's probably not going to be that kernel. But the point is it actually does correspond to a space that we use all the time for doing estimation. So it may not be obvious what the kernel is, or conversely, given a kernel, it may not be obvious what the space is. Luckily, these things have all been worked out for us for most of the common things that we're going to be dealing with. Okay. Finally, a couple more things, and then we'll have all this background stuff done. Actually, I think I did this for a particular m. This looks to me like 1 or 2. Let's see. Oh, this is 1. Yes. Yeah. But let me mention the last thing we're going to mention about these spaces for now. We'll talk about them more when we need them. But this one, I think, gives a lot more intuition about what the functions look like, which is, remember we talked about the eigenfunctions. So I can take, just like this was a matrix, except it's an integral. So instead of matrix multiplication, we're integrating, but we can still talk about the eigenfunctions and the eigenvalues. Okay. And the kernel, and it may or may not be possible, by the way, to actually find these eigenfunctions, right? You'd have to solve this thing. So for very specific spaces, we can write down explicitly what these eigenfunctions are. In general, it might be difficult. But let's just not worry about the actual computation. What's useful here is that you can always write the kernel as this infinite sum. And you can also expand the functions So another way to think about reproducing kernel Hilbert spaces, these functions actually form an orthonormal basis for this function. So just like, a lot of times you create a space by just making, a set of basis functions. That's what's going on. These eigenfunctions just form a basis. And in some sense, you often hear, like when people talk about using these things for classification, they talk about the feature map. They just mean, given an x, so the feature map is simply defined to be these terms here in this expansion. It's kind of an interesting thing because now you can see that the inner product between two functions is really just the inner product of these feature representations. One of the things you hear about is this in the kernelization is you're really, when you take a support vector machine, you replace an inner product with a kernel, what you're really doing is mapping the data into an infinite dimensional space, which seems like a funny thing to do because how can that help you to make the dimension higher? But in this particular case, that's actually what you're doing. So what you're really doing is kind of working, you can think of yourself as working with the x as the original data and using a reproducing kernel Hilbert space, or you're mapping the data into this higher dimensional space and just using ordinary Euclidean geometry. But so this is conceptually useful. No, you wouldn't actually compute anything this way. So let me say it another way. Any f we know can be written as some combination of these kernels. But it can also be written again, if we wanted to, as a linear combination of these basis functions. This is a more traditional and simpler way to think about a function, right? Just I expand it in some basis. It's just that this is not a convenient thing to work with. This is much more convenient to do calculations. But if it ever gets confusing, just think, oh yeah, it's some linear combination of these basis functions. In fact, you can even rewrite the inner product. From this representation, we can rewrite the inner product. We can write it in terms of the kernel like we originally did, but if we just replace the kernel with this function, that's equivalent to just doing this. Let's suppose f and g, I expand them and they have coefficients, let's say aj and bj. These are the eigenvalues. That's another way to write the same inner product. So in other words, if I wanted to get the inner product, I can use the kernel formulation I first told you about, or I could say, no, I'm going to expand it in this eigenbasis, and then I can use the coefficients in that expansion to compute the inner product. And typically what happens is because these are the smoothness of the function, to keep this finite, these have to die off pretty quickly. That's where the smoothness comes from. But we're never going to actually compute it this way. I don't know if that helped or hurt, but we're never actually going to compute it this way. We're always going to be working with the kernels because that's the advantage of the kernel representation. Okay, in particular, the norm of f squared, if I expand it in this basis, I'm going to get this for its norm. Typically, these eigenvalues are getting smaller and smaller and smaller. Right? You have the first eigenvalue, the second eigenvalue, they get smaller and smaller. So how can this stay finite? These coefficients must be going to 0 pretty quickly, right? Otherwise, this would blow up. And if you think about these functions as looking like sines and cosines intuitively, what that's saying is you've got to be putting lower and lower weight on the higher and higher, wigglier and wigglier functions. And that's why the functions in this reproducing kernel Hilbert space are smooth. So I don't know, I was just trying to give you some intuition about what these functions look like. We will, at this point, we're going to return to this when we get to regression, because we want to compare when we do regression. I mentioned this Tuesday. We're going to compare two methods for doing nonparametric regression. Local smoothing, where you just take your y's and take an average locally, very simple, versus minimizing the sums of squares subject to the regression function being in a reproducing kernel Hilbert space. They're very similar, but they're not quite the same. And we'll talk about the advantages and disadvantages of the two approaches. The short answer is local smoothing is actually better, despite the popularity of reproducing kernel Hilbert spaces, but that's just my opinion. Okay, we'll get to that next week. So that was a real fast crash course. I realize I went quickly. The main thing is really to have all these notes as a reference. So if you hear me mention an RKHS or a holder condition, you can look back at it as needed. All right, it's not that you need to be an expert in this stuff for this course. But now I can mention them without feeling guilty. That's really the most important thing. Any questions?
People compute this in real life with an approximation by summing it to some large or finite value?
No, people compute it using this formula. That's one of the beauties of the kernel representation, is you can avoid having to deal with the eigenfunctions and so on.
Technically, if we want to calculate the inner product, how should we do?
By using the definition that we first put down, which is this one.
Since there is a completion of H0, in general, I think it cannot to write in that.
Well, when we go to do this, so this is actually in the notes, but it's also on the homework. Because, for example, when are we going to need to do this? Let's say I need to do the regression problem. It turns out, due to the representer theorem, you never need to do any calculations other than at the observed data. That's another beautiful property of these kernels. So all the calculations become finite dimensional, even though we're doing technically an infinite dimensional space. You'll do that on the homework. It's not difficult. It all comes from the elementary properties of the reproducing kernel Hilbert space. Yeah, it seems like you're doing some sort of infinite dimensional calculations here, but when you actually go to do this on any data set, you can prove the minimizers of the things you're interested in only involve the kernel evaluated at the data point, so it becomes a finite dimensional minimization.
Sorry, can you just quickly go through again why the norm being smaller implies that the function is like still not quite.
Well, yeah, I was being a bit loose there, but what do these eigenfunctions look like? Well, it's hard to say because it depends on the kernel. But let me show you what typical eigenfunctions look like. The first one might look like this. The second one might look like this. Third one might look like this. They typically get more and more wiggly as you go further and further down into the series. And the eigenvalues are decreasing. So what's happening is to keep this finite, the AJs have to be getting small, which means these higher order wiggly functions are going to get very little weight. That's the intuition. Okay. Okay, once again, don't worry, if you've never seen it before, don't be overwhelmed by the details. We'll refer back to it as needed. It's not a big deal, all this stuff, yeah.
If we consider about a common LP Hilbert space, what's the evaluation function of that space?
In the LP space?
Yes.
Well, the evaluation functional is just defined to be the functional that returns the value of the function, but it won't be continuous functional in any of those LP spaces in general. Yeah.
You mentioned that the evaluation functions are continuous.
Yeah.
Continuous with respect to what?
Oh, what I meant was, if in general, if Fn converges to F, yeah, I wasn't clear about that, and I have some operator of any kind, the operator is continuous if whenever Fn converges to F, T of Fn converges to T of F.
Oh, so the same one we
Yeah. Okay, don't sweat it. If you haven't seen it before, it's not a big deal. So if there's no other questions, I really want to move on to some more interesting stuff. Because I don't consider that stuff interesting. I don't know about you, but to me it's like the necessary background you got to have. So it's the vocabulary we need. Okay. Now we get to something interesting, which we've done some part of it in 705. So most of you have taken 705. For the few of you who haven't, you really, I'm assuming you know this, because the first part I'm going to go through real fast because we've already done it, which is concentration of measure. And this gets used in lots of places in stats and in ML. It's a good tool to know. The main thing we want to take away, before I plunge into it, there's really two big takeaway messages, which is, what is the Rademacher complexity? I want you to know what that is because you're going to see that in NIPS papers and things like that. And second of all, we mentioned there's something called the VC theorem in 705. I'll remind you what the theorem is, and then we're actually going to go through the proof. So, you know, I try to make choices about what proofs to do because there's nothing more boring than watching somebody else go through a long proof on the blackboard. I don't like it. I assume you don't like it. Proofs are better done at home, with a fire going, glass of brandy. Okay, this is what I recommend. You have to really think about it. But there's some that are worth seeing, you know, because the techniques in them get used a lot. That's to me what makes it worth going over. So we'll do the proof of the VC theorem. Some of you have probably seen it before, but I think a lot of you have. Who has not seen it before? Okay, yeah, there's maybe half. Some of you are afraid to raise your hand. We'll go through it. I think it's worth seeing. It's not that long, and there's some good tricks like symmetrization and so on that you're going to see a lot when you read papers. So I think it is worth doing the VC theorem, and it's just such a famous theorem, and it's a very cool theorem, so we'll do that. There'll be some other results here, too, that we'll just state without proving them. So concentration of measure. Let's remind ourselves what it means and why we care about it. And don't worry, after we do concentration of measure, we're going to switch over to more methodology. We're going to talk about regression, high-dimensional linear regression. So we'll get back closer to the real world and do some more methodology stuff. Then we'll come back and do minimax theory when you're trying to do more of the abstract stuff. Okay, so concentration of measure, remember, just means that some random thing concentrates around its mean, typically. And that's often a very, very useful thing for understanding the properties of things. So let's just review some 2 or 3 examples of where we would use this. Well, the most famous one that you all know is classification. So, and in particular, if you do empirical risk minimization. So we have these data. The y's, let's say, are 0 and 1. And if you have a classifier, which maps some x, any x into 0 or 1, then we have that the prediction risk is the probability of making a mistake on a new example. So whenever I write that, x and y represent a new pair. And of course, we don't know this because we don't know the distribution, so we usually use the training error, which is just the observed average. That's the indicator function. Now, if all we had to deal with was a single classifier, we would know that this empirical error is close to this because of Hoeffding's inequality. Let me remind you of Hoeffding's inequality. That now should be pasted in your memory, but if it's not, go back and review it for 705. Hoeffding's inequality says that the probability, so let's take a bounded random variable. Let's say that the average minus the mean, the probability that that's bigger than epsilon is less than or equal to 2 times e to the minus n epsilon squared times some constant which involves how big the endpoints are. That was Hoeffding's inequality. So again, if you forget it, you should go back and review it because everything we're going to use now depends on Hoeffding's inequality. Most of concentration of measure, to some degree, is just extending Hoeffding's inequality. And that says that the average compared to the mean, the probability that they deviate by more than epsilon is very small. The fact that this goes to 0, remember, exponentially quickly is what makes it very useful. And this, so we could apply that here. These are just coin flips. These are zeros and ones. And so there you go. The probability that the classification error and its estimate differ by more than epsilon is very small. But remember that the reason why it wasn't that simple was because when you do empirical risk minimization, we're going to choose a classifier. We're not given a classifier H. We're going to choose it over some space. So the way I like to draw it, if I can just pretend that each point on the x-axis is a classifier, then there's a true risk function, which I don't know. For any classifier, I can estimate it. So maybe my estimate looks like this. And so far, all we know is that these are close at any one given point with high probability. But since we're going to choose the classifier that minimizes the arg min of H over some set of classifiers of the empirical risk, so that's your empirical risk minimizer, we want to guarantee that that has good risk. So remember what happened was that if there's a lot of places for this to fluctuate. The only way we could make sure that the minimizer of the empirical risk also has good risk is to make sure that these two curves are close everywhere. Remember, we wanted uniform. We talked about that quite a bit, right? We wanted uniform convergence. So we wanted to say that the probability that the sup we wanted this to be small. And what we ended up with was some measure of complexity, I'll put it there, times something exponential. That's the Hoofding part. But this is the price you pay for the fact, remember, that we were taking the maximum over a set of things. And that's what we want to talk about in a little bit more detail. There's lots of other cases of concentration of measure being useful. You might want to look at these other examples. I won't do them. But k-means clustering, you're actually minimizing some sample quantity. But there's actually a population version, and you'd like to show that they're close. And later on, we'll actually prove that that's true using concentration of measure. Cross-validation. When you're using holdout data, of course, you're hoping that the risk estimate you get is a good estimate of the true risk, especially if you're using cross-validation for choosing a tuning parameter. So think about something, a classifier or a regression estimator that has some sort of tuning parameter that you have to pick, like a regularizer, for example. And if we use, say, some holdout data to choose that, we need to make sure that the risk estimator we're getting from the holdout data is close to the true risk uniformly over that tuning parameter. And so that's the kind of thing we're going to have to prove. I actually have that written out in some detail on page 2, which I'm not going to go through on the board now. I'll go through it when we actually get to it. I wrote out two really cool theorems, one for regression and one for classification, that shows that choosing tuning parameters from cross-validation actually works, that justifies it. And the justification is these tools, concentration of measure. So let's do it. Let's get into what we want to do, concentration of measure. And as you're going to see, I'm going to skip a lot because the first part is all about Hoofding's inequality and Bernstein's inequality. Did we do Bernstein in 705? Homework. We didn't? Homework. See? He remembers.
There's just a homework comparing
Yeah, okay.
behavior of
All right, but you've heard of it. All right. The key, more importantly for us, though, is Hoofding's inequality. So I'm assuming you remember that. Let me just, though, write down some. Do I need this notation yet, actually? Actually, we don't. I'm going to jump. So I'm going to jump right to page 9. No, don't worry. You already know the other stuff. It's just hoofing. Just read through it quickly at home. You're not missing anything. I promise. It'd be really boring if I did that again. Okay, what I want to start talking about though is going beyond what we did in 705. So we know we want to get some sort of theorem like this. We even mentioned one in 705, which was the VC theorem. Now I want to build up to that. Build up the pieces we need to actually state and prove that theorem. So what goes out in front in any of these things is some measure of the size of the class, the complexity of these class we're dealing with. Actually, I guess I am going to need, do I need this notation? All right. Let's see. So I have some class of functions. It doesn't have to be classifiers now anymore. So it's just some class of functions. Let's call it script f. Inevitably, I'm going to take some average. For any one of these functions, there's an average. That's what we can compute from the data. And then there's its true average, the expected value of f of x. Okay, and we know, let's say it was bounded, so we know from Hoofding's inequality again that this is close to this with high probability. But we really want to look at how close is this over the whole space. I want to look at, let's just call this mu sub f. I want to look at this. Our goal is to bound this. Okay. So it's going to depend on how complex f is. And the first measure that we're going to use is Rademacher complexity. So let's define that. And here it is. What we do is we're going to create new random variables, sigma 1, sigma 2, sigma n. They're called Rademacher random variables. They're IID. They're independent of everything else. And they're equal to plus 1 or minus 1. So just imagine generating coin flips randomly. And then the Rademacher complexity of the class of functions is defined as follows. What you do is you take sigma I so we take the average that we're interested in, but we throw in these random sigmas. And now I take the maximum over all f's in f. All right. That's the definition. So for those of you who have not seen this before, let me just unpack this a bit for you. Okay. The definition is an example of something that comes about that it turns out it's really something that occurs in the proof. And so when you need something in a proof, at some point you say, let's just define it. Let's just call that something. I think that's where it came from. Because you're going to see we're going to use it in the proofs. But it actually does have an intuitive meaning. Why in the world would this measure the complexity of class of functions. Well, let's think about it for a moment. Let's take a simple example of a single function, f. So there's no soup here. Okay? Then if I look at this, well, this is just f at some value, f at some value. These are +1 and -1. Basically, these are going to be positive and negative, with equal probability. So this is like a mean zero random variable. And what happens when I take an average? The variance is like 1 over n. Right? This is like having like an x bar with mean 0 and the variance of x bar when we did calculations like that was some constant over n. Right? Take an average of something, mean 0, just like we did in 705. Right? This is plus or minus 1 with equal probability. Mean 0, it's an average of mean 0 random variables. It's like saying x bar has mean 0, variance 1 over n. This is going to be very small. Well, in fact, its variance is 1 over n. So what did we learn about something like that? We learned that was roughly of size. Then remember this big OP stuff that was like, right? That, yes.
Are these set i's fixed?
ZI's are not fixed. They're also random. There's two versions, I should say. There's the data-dependent version where the z's are fixed, and then there's the version where they're not fixed, which you can think of as a second expectation.
Then you take the expected value with respect to the measure of the sets.
So when we take the expected value, it's over both the sigmas and the f of z.
And they're independent.
And they're independent, though. Yeah.
And this is for binary classification.
No, this is just for arbitrary functions right now.
F can go to the real.
Yeah. We're going to stick to probably bounded functions. OK, so what I'm trying to convince you is that if it was only a single function here, this is going to be like something like of order 1 over the square root of n. This is going to be like 1 over root n. Did that logic convince you? Maybe I should make that a homework question to actually prove this. It's not hard. That this is going to be a small quantity if there's just a single function. Because it's just there's no soup anymore. It's just an average of something with mean 0 and variance 1 over n. That's all I'm saying.
Wouldn't that make the expectation 0?
Pardon me?
Wouldn't that make the expectation of that 0?
Yeah, I'm being not quite, because there's a absolute value here, but I'm being just very intuitive here. Right? It's not exactly 0. Yeah, the expected value of the inside is 0. So this is not a proof. I'm just trying to give some intuition that this is kind of small. However, let me now try to give you the intuition of why, if f is a very complex set of functions, this is not going to be small. Okay, think of f as having lots of wiggly functions in it, for example. Well, what are we doing? If you think about your sigmas, they're +1 and -1, and they're random. So maybe I get a +1, +1, -1, +1, -1, +1, +1, -1, who knows what it looks like, right? Now, when I take this average, I want to make this as big as possible. How could I make that big? Well, I get to take the soup over f. Imagine it's a game, and you generated the sigmas and the z's, but I get to pick an f in that function class. And how could I make that big? I could make that big if I can find an f which matches the sign of your sigmas, that goes up whenever this is here and goes down whenever this is here. Then we're not going to get pluses and minuses canceling out anymore. This is just going to keep adding up, and you're going to get something like maybe of order n even. Well, that's exactly what it would take. What would happen if we had a sufficiently complex class? I could find an f that goes like this, maybe like this, then goes down like this, down like this. In other words, I could keep tracking your sigmas with some f if f is a really complex class. Has lots of wiggly functions in it. Then I can keep doing that, and that means whenever this is negative, whenever this is positive, they're always the same sign. I'm adding n of them together. This is going to be kind of big.
Is there any constraints on the random variable z?
Right now, there's no constraints on these random variables. They're IID. That's all. Again, this is just meant to be some intuition that if script f has a lot of complicated functions in it, this could potentially be a large number. Another way to look at it, by the way, is I'm just taking the correlation between f and these sigmas. And if the maximum correlation between f and these are just noise variables, they're just random. If the maximum correlation between your function class and noise is high, again, that means that somehow I can correlate myself with any random pattern that suggests f is filled with complicated functions. Okay? So that's the intuition. I mean, obviously, for this to make sense, we have to compute the Rademacher complexity in particular cases. Unfortunately, as you'll see, there's some cases when it can be computed, but most often it cannot be computed. It's upper bounded by something which is computable, like the VC dimension. Okay, so, but it's a more fundamental quantity. So even if we can't actually compute this, it's a very fundamental quantity, and it's kind of a, I hope it seems now kind of like an intuitive way to measure the complexity of the class. All right, so having defined it, you can check, and this will probably be homework, that it satisfies some fairly intuitive properties which are listed here in lemma 14. Well, first of all, if I make the function class bigger, so if f is contained in G, then this can only get bigger. Okay, here's another. This one's actually kind of interesting, which is the Rademacher complexity of f is equal to the Rademacher complexity of the. And what this is the convex hull, all linear combinations of convex combinations of functions in there. It doesn't change the Rademacher complexity. That's worth thinking about for a second, because what that's saying is if I have some points, think of them as points, and I fill in the convex hull, I'm actually filling in quite a bit sometimes. But that doesn't change the Rademacher complexity. And that's because the extremes haven't changed. So that's kind of saying maybe this is a good measure of complexity, because you don't really want the measure of complexity necessarily to go up just because you add in linear or convex combinations of things. Other measures of complexity do increase when you take convex hull. So this is some notion that maybe we're measuring something good here. Okay, and finally, another useful one is that if I have a Lipschitz function, let's say g, which is 0 at 0, and Lipschitz what happens if I take so imagine if I take the function class, now I apply g to every function in that class to get a new function. So we'll write that as g compose f. I mean, in general, you think, well, who knows what that's going to do to the complexity? But it turns out that at most, that increases by a factor of L. So that might be a useful thing to know, because it might be that the original class, it might be that the, you start with a class, then you want to apply a transformation to it. As long as the transformation is nice, that's saying, you can't change the complexity of the class too much. Okay. So what's going to happen is in a lot of the proofs, it's just going to be, because of the proof technique that Vapnik invented, I think it was Vapnik who invented it, this quantity is going to arise naturally, right? My guess is he didn't sit down one day and think, I think I'll invent this notion of complexity. I really think it emerges from the proof. I can't say that for certain, but I think that's what happened. But before we jump into the proof of the VC theorem, which is what our goal is, let me relate it to what you already know, which is VC dimension shattering number. So let me remind you how that works. Okay, so just to remind you, suppose f now is a set of binary functions. So notice I didn't require the functions to be binary. But now I'm going to stick to binary functions. What that means is, you know, f of z is either 0 or 1. So the obvious example being classifiers. And I'm going to have a set of those. And now we're going to talk about a little bit of notation is people usually write script f sub z1 to zn. This is a finite sequence of points. That just means take each function and evaluate it at those points. So that becomes a set of vectors. It's called the projection onto the points, right? Just take each function, evaluate it at a given set of points. That's a vector now of length n. The set of all such things as I vary from the function class, that's just a set of vectors now. Okay. And the shattering number is the number of such vectors. Where did I define that? I think I forgot. Oh, it's on the next page. So the shattering number, we talked about this in 705, and I'm sure you talked about it in 701 or 715. It's just the number of such vectors. So it's the maximum over all choices of finite choices of z1 to zn of those projections. Does everybody remember that? Shall I review an example? Yeah, so you're right. There's different ways of saying it, which is how many ways are there to pick out things in the set? They're the same thing, right? Because when you say, how do I pick something out? That's just like creating a vector of zeros and ones of whether it's in the set or not. And a set is a function, a binary function. A set you can think of as an indicator function. Let's just do a simple example just so make sure we all remember. Okay, I mean, I have an example right here. So just so we're all on the same page, let's take this set of functions. So these are functions indexed by the reals, and they're defined as follows. They're equal to 1 if z is bigger than t and 0 otherwise. So these are like binary, a very simple classifier. So 0 and then 1. That's a typical function. Again, you can always think when you talk about this VC theory as binary functions, or if you prefer sets, just think of this as a set, this set here. And a binary function you can think of as the indicator function for a set, either way. But I'm just calling them binary functions here. As I vary t, I get a different function or a different set. And so this is a collection of sets or a collection of functions. And let's remind ourselves in the last few minutes then what the projections look like and what the shattering numbers look like. So if I pick, and remember you have to do this for, let's do, what did I do in this example? I did for n equals to 3. You have to do this for each n, and for each n, remember, you have to consider every possible configuration of finite points. Right? It's a worst case analysis. So let's pick an arbitrary set of points. We call them z1, z2, z3. And then, of course, now I'm just going to ask myself, as I sweep through that class of functions and I look at the corresponding projections, what possible vectors can I get? Well, if that cut point was here, I get 0, 0, 0. If I move it here, I get a 0, 0, 1. And then I can get a 0, 1, 1, and then 1, 1, 1. right? That's the set of possible projections. And you can see that's true no matter how I pick z1, z2, z3. So the shattering number for n equals to 3 is 1, 2, 3, is it 4? 4. What is the biggest it could possibly be? 2 to the n, right? The highest it could be would be every possible binary expansion. So we always know this is less than or equal to 2 to the n. Hopefully this is all, coming back to you if you've forgotten it. Any questions here? Okay. So the shattering number is another measure of complexity. And Theorem 16 reviews some properties of shattering numbers. You already proved those things in a homework in 705. I won't go through them. But here's the theorem we want to prove, which is that the Rademacher complexity of f is less than or equal to 2 times the log of the shattering number over n square root. This is actually not the tightest possible result, but it's a fairly easy one to prove. So what's the purpose of this? The purpose of this theorem is that, as I said, this might not be easy to figure out. But this is something we know what the shattering numbers are often for a lot of common classifiers or classes of functions. Now you might wonder to yourself, but if we're just going to upper bound it with the shattering number, why introduce the Rademacher complexity at all? But there's two reasons. One is, again, you're going to see it comes up naturally in the proofs. And second of all, there are cases where it's tighter and it leads to better results. So we'll see this when we talk about k-means clustering. If we use VC theory to do k-means clustering, we're going to get a certain rate of convergence. But now you can ask, what happens if the dimension of the space is really high? It turns out that the VC approach gives a terrible, terrible rate. If you use the Rademacher approach, we get a much, much sharper rate. So there are really important cases where the difference between these two things it's strict and it gives a much better answer. Okay, so we are going to use an upper bound for now, but keep in mind that that's for convenience, and it's not always the case that we want to use the upper bound. So let's see if we have time to. We can start the proof. I hate to start a proof. Actually, rather than start it, we'll do the proof next week. Instead, I want to remind you now what's the definition of the VC dimension, which is, just to remind you, we know that the shattering number is always less than or equal to 2 to the n. Here's a picture I drew last term. Was if this is n, and this is the function 2 to the n, and if I now draw the shattering number as a function of n, remember what happens is it can't be bigger than this, but it doesn't have to stay equal to this. It could be equal, and then it could be less than, well, I don't want to draw it like that, less than this. And this is the VC dimension. So the VC dimension is the largest n, the maximum n, such that the shattering number achieves its maximum. Okay, and I'll remind you next time that one of the astounding, I think astounding theorems is Sawyer's lemma, which says that if, so first of all, the VC dimension might not be finite, and we'll see examples of that. But if it is finite, if this does occur somewhere, then the remarkable thing is the growth of this is exponential, and then all of a sudden, remember, it becomes polynomial after that. It becomes like what? N to the VC, right? Which is really, to me, that's an astounding fact. Why would it switch from exponential to polynomial? I mean, it does, but it was not something you would have guessed ahead of time, I don't think, and it's what makes a lot of machine learning work. So that's why it's useful to have classes with finite VC dimension. But we will be talking about things later in the course, many things, where the VC dimension is infinite. And you can still say lots of things in that case. Like in regression, lots of the classes of smooth functions that we deal with do not have finite VC dimension. So always bear in mind that finite VC dimension is helpful, but not necessary. Okay? So are there any questions? Yeah.
I might be wrong, but in Zonify, I don't think we were restricted to binary functions.
For VC?
Yeah.
Well, there is a way to define the VC dimension of real valued functions in terms of their subgraphs, but I think we restricted ourselves to binary functions. If not, we are going to restrict ourselves here for convenience to binary functions. Yeah. Your memory is probably better than mine, so I trust you about what we did in 7. It's sad that I taught the course and he remembers more about it than I do, but that's not unexpected. So what we'll do on Tuesday, so look through the notes. We're going to go through theorem 17. Okay, then we're going to jump to theorem 21, which is the big theorem, the Vapnik-Chervonenkis theorem. We're going to go through the proof. It's not, it's not too difficult. It's got some cool tricks in it. Then we'll do a couple of examples. Okay, and finish that up. And keep an eye open. Remember, the assignment 1 is posted, and I'm going to post the notes on regression. Probably going to cover regression much differently than you did in 701 or 715. And for those of you who took 707, it'll probably also be a bit different, because the big difference is P is not equal to NP. No, I was just trying to see if you were still paying attention or not. The big difference is we're going to do it in a completely distribution-free way, model-free way. No assumptions about the model. Okay? Any last questions? Yeah.
Any updates on the wait list?
Oh, any updates on the wait list? No, there aren't. Right now, let me count. 1, 2, 3, 4. 4 people don't have seats, right? How many open seats are there? More than 4. So, in principle, if you guys are willing to squeeze in, you're all, I mean, I don't like, if you want to sit on the stairs, it's fine with me, but I think you'd be more comfortable in the chairs. But if it's true that I can fit everybody in, then I'll just clear the whole waiting list. But I want to be really sure about that first. So hang in there. If you're on the waiting list, though, it's looking to me that with high probability, I can get everybody into the class. Okay? Based on the data available to me here.